Hi all. So today in this session we will be dealing with relationship between SVD and rank of a matrix and also how to find the pseudo inverse of a particular matrix. Okay, so before that let's recap Voodoo singular value decomposition. Suppose you are given a particular matrix A, let it be M by N matrix, then it is possible for you to write A as the product of three matrices, which is U, sigma and V transpose, where U, if A is M by N matrix, then U will be an M by M square matrix, then your V will be an N by N square matrix and your sigma will be an M by N matrix. So you will have to note that, okay. If A is M by N, your U will be M by M, your V will be N by N, and your sigma in between that will be M by N matrix. So you need to remember this order. Then only you will be able to form the singular value decomposition. Okay, now using this particular singular value decomposition of a matrix, we will be able to find its inverse. Not the proper inverse, but we call them a pseudo inverse. Okay, so we'll just see how to get the pseudo inverse. So for that, suppose this is our sigma and let the diagonal entries in the diagonal we have the singular values which depends upon the rank of A, and we'll just arrange them from the descending order and we'll see how can we get the pseudo inverse. Before that, let's see how to find the rank of a particular matrix. So there are many methods to find the rank of a particular matrix. Basically, the definition of rank of a matrix is the number of linearly independent rows or the number of linearly independent columns. But in our problems, we will be just finding. We know how to in the singular value decomposition, we will definitely find A transpose A and get a square matrix, right? And we'll be finding the eigenvalues and correspondingly we will be finding the singular values taking the square root of eigenvalues. So the number of non-zero singular values is in fact called as the rank of a particular matrix. Okay, suppose if you have your eigenvalues to be 4, 3 and 0, let it be a 3 by 3 matrix, then your sigma i's will be root 4, root 3 and root 0, which is 0 itself. So the number of non-zero eigenvalues, singular values, that is equal to the rank of A. So here for this particular 3 by 3 matrix, the rank of A will be equal to 2. Okay, so we'll just see the number of non-zero singular values and that will be the same as number of non-zero eigenvalues of A transpose A. Okay, so we'll just find the eigenvalues of A transpose A and get the rank of A. That's how we usually get rank of A, and we'll just discuss this in coming problems. And now we'll just see how to get the pseudo inverse. So for pseudo inverse, the pseudo inverse of a particular matrix A is denoted by A plus. We'll have a plus on the top. Okay, this is called the pseudo inverse of A. And the pseudo inverse of A is given by, we'll find V, which was an n by n matrix, and U, which was an m by m matrix. If A is an m by n matrix, we know how to find V and U and sigma also. So your A, the pseudo inverse which is denoted by A plus, is given by V sigma plus U transpose. Okay, so we have V, we have U, but we don't have U plus sigma plus, right? We'll just see how to find sigma plus. That is, we have sigma. If suppose your sigma is equal to say 2, then rest are zeros. Let it be 1, then rest all zeros, and let it be 0, 0, 0. And let me have one more 0, 0. Okay. So now it's yeah, better this is, let us make this one. Okay, let's remove the, yeah, now we have a 4 by 3 matrix and the corresponding sigma plus is given by, if this is the sigma of a particular matrix, the corresponding sigma plus is given by, you'll just take the reciprocal of the diagonal entry. Okay, non-zero diagonal entry, that is first one will be 1 by 2 and here it will be 1 by 1, so it will be 1. Okay, then what happens is, if it is a 4 by 3 matrix, you do 3 by 4 by making all other zeros. Okay, so to make it 3 by 4, you will have 4 columns and 3 rows. Okay, so this is your sigma plus. This is how you, if you have the sigma, this is how you get the sigma plus. And we write it generally as the diagonal entries will be 1 by sigma 1, 1 by sigma 2, till 1 by sigma r, and the rest all are zeros. Okay, this is how you get your sigma. And you should always remember that V is an n by n matrix and U is an m by n matrix if your A m by m matrix if your A is an m by n matrix. Okay, just remember this order that is necessary for you to do the problems. And now you have the rank of the pseudo inverse. And how, what is the rank of the pseudo inverse of a particular matrix? Rank of A plus is still equal to rank of A. Okay, they both will be having the same rank, that is they have the same number of non-zero singular values. Okay, and now why do we need the pseudo inverse? The thing is, actually, if before that, if rank of A is equal to n, suppose A is an n by n matrix, A is an n by n matrix, and rank of A is also equal to n. If it is a full rank matrix, then definitely it will have an inverse, right? Its determinant will be not equal to 0 and it will definitely have an inverse. And at that particular time, your pseudo inverse, what you get by doing that U sigma plus V transpose, by doing this you will be getting a plus, and this particular A plus will be equal to the original A inverse. Okay, if the inverse of a particular square matrix exists and if its rank is full, then its inverse and its pseudo inverse will be the same. Okay, and if it is not having the full rank, let A be an n by n matrix or let A be an m by n matrix, and if it's not a full rank matrix, still, then what happens? A inverse do not exist. Okay, the determinant will always be equal to 0 and we will not be able to find the A inverse. But what happens here is we can find the pseudo inverse in this case. Pseudo inverse exists in every order irrespective of the rank. So that is the advantage of pseudo inverse. So that's why we need to find the pseudo inverse of a particular matrix. Okay, in case the matrix has an inverse, pseudo inverse will always be equal to that inverse, and if it does not have an inverse, then we'll just have pseudo inverse that in that case. Okay, that is the advantage of finding the pseudo inverse. Yeah, now we'll just do a problem to find the pseudo inverse of a given matrix A is equal to 1 0 0 0 2 0. So first we'll have to find we'll have to find V, we'll have to find V, we'll get U, and also we'll have to get sigma. Okay, and then we'll find sigma plus and just we'll do the product and get over the pseudo inverse. So to get V, what was V? We need to get A transpose A, and we need to get the eigenvalues, we need to get the singular values, when we need to get the eigenvectors and then arrange them in the column wise to get V. And what was U? Ui is equal to 1 by sigma I AUI, which we, sorry, AVI, which we have already discussed, and we also know what is sigma, writing the diagonal entries, right? Yeah, so let's try to find A transpose A first. What is A transpose A equal to? A transpose A is given, so A transpose A is 1 0 0 0 4. So it's easy to find the eigenvalues. Eigenvalues will be the diagonal entries. Since it's a diagonal matrix, eigenvalues will be 1 and 4. Okay, now we have the eigenvalues, and now, yeah, eigenvalues are here. Now what to find? To get the eigenvector. So when lambda is equal to 1, you will have just do A transpose A minus lambda I into V is equal to 0. So we have lambda equal to 1. So we have this particular matrix into V is equal to 0. So this will imply 3 into y is equal to 0. So your V1 will be 1 and 0, and correspondingly just for lambda equal to 4 also just find the eigenvector, so you will get 0 and 1. Okay, so then we'll form V by, how will we form V? Just write V1 here, just write V2 here. We need to normalize them before before getting V, but to normalize here it is equal to root of 1 square plus 0, which is equal to 1, so you'll have to divide by 1 only. So this will be the same V1, so just write it as column. Okay, so now we have this, and also your eigenvalues was equal to 1 and 4, right? So lambda 1 is equal to 1, so your corresponding sigma 1 will be root of 1, which is equal to 1, and your lambda 2 is equal to 4, so your sigma 2 will be root of 4, which is equal to 2. So you have your singular values to be 1 and 2. And this A transpose A was a 2 by 2 matrix, and you had two non-zero singular values, right? Non-zero singular values, so their rank of A is equal to 2. Why? Because since you have two non-zero singular values. Okay, non-zero singular values. Okay, now you can find, we have V now, then we'll get U. Okay, so how will we get U? U is Ui is equal to 1 by sigma I into AVI. So coming to first one, U1 will be 1 by 1 into A into VI. Will be getting this particular matrix. Okay, since your A is, I think A was 2 by 2. Oh, I'm sorry, I think I just, yeah, A was 3 by 2, right? 3 by 2 into 2 by 2 will give you, sorry, 3. This is your A was 3 by 2 and this is a 2 by 1 matrix, so you will be getting a 3 by 1 vector. So this is your U1, and you can also get your U2 by doing the same way. And see, your A was 3 by 2 matrix, so your U should always be a 3 by 3 matrix. Okay, so to form U, you have the first column to be 1 0 0, and you have the second column to be 0 1 0, and you need a third one. So what we do is we'll just choose an orthonormal vector to both of them. Okay, how do we get an orthonormal vector? So we need an orthonormal vector to both of them. So what we do is we need we need to multiply 1 into C1 plus 0 into C2 plus 0 into C3 should be equal to, or else we don't need that. As we know, these are the standard basic vectors. You know, a vector which is linearly independent to 1 0 0 0 1 0, that will be definitely be 0 0 1. So choose, you can randomly choose a third linearly independent orthonormal vector. Okay, it should be orthonormal, which means that root of 0 square plus 0 square plus 1 square should be equal to 1. Okay, since it's equal to 1, your third vector is also orthonormal, so choose this to be your U. Okay, so now you have U, and since by using your U was equal to I3 and your V was equal to I2. Okay, and your sigma, what will be your sigma? How do you get the sigma? Sigma, first you will be writing the first singular value, which is 1, and then zeros. Okay, just before writing the zeros, we have the second eigenvalue is 2. Second eigenvalue is 4, therefore the singular value is 2. Okay, then write the zeros. Since A was 3 by 2 matrix, so your sigma will be this one. And now how do you get sigma plus? You just rotate them. Okay, and take the reciprocal of the non-zero diagonal entry. So 1 by 1, here it will be 1 by 2. Then just take, since it was 3 by 2, make it 2 by 3. So just 0 0. This is how you get sigma plus. Okay, and you need, what is your pseudo inverse? E plus is equal to, it was V sigma plus U transpose. Okay, but your U transpose, U was 3 by 3 matrix, which is the identity matrix, so this is identity, and V was also an identity matrix, so your this will basically be equal to your sigma plus, so your A plus the pseudo inverse is equal to 1 0 0 0 1 by 2 0. This is your pseudo inverse. Okay, so hope you got the problem, the idea of the problem and the steps of the problem. Now we will be